Hello, this is Mariam. I'm gonna present my assignment 3 in hardware security course. At first, I'm gonna tell you some outlines and goals and some definition. Our goal in this paper is reconfiguration of some IoT modules. This reconfiguration is related to dynamic part of it. And researchers have focused more on standardizing the IoT architecture for connecting systems into a unified infrastructure. At first, I'm gonna introduce some meaning like CHS. CHS, or cryptographic hardware solution, means all of this definition: hardware security module, secure crypto processors, tamper-resistant security module, crypto accelerators, and embedded crypto engines. And now I'm gonna define an IoT. The IoT, or Internet of Things, is a foundation for connecting things, sensor actuators, and other smart technology to have some connection between person to object or object to object. This model is connected graph in which each application utilizing the cryptographic services are on one side and the CHS on the other side. In this paper, an IoT architecture has been defined which supports dynamic partial configuration, part or DPR, to the hardware components. The dynamic nature of IoT demands online modification to both the hardware and software components. It means that by putting a dynamic part beside the static part of an IoT infrastructure, we can have some modification online, and it means that adding or removing some hardware from our architecture. This DPR architecture is the basis of hardware sharing, hardware mixing, and online hardware updates. And each FPGA is programmed with more than one CHS. The question is appeared here is how DPR is performed in this proposal architecture. We can apply modification into the DPR by high-speed, low overhead transferring the required partial configuration bit stream over a live network connection to the FPGA. It means that we are going to apply some predefined bit stream number after a predefined time to our FPGA board. Enabling DPR on a FPGA requires partitioning the FPGA logic into static and dynamic partition. As I said before, the only part of our architecture that can have endure some modification is a dynamic part of it. The dynamically configured modules can reside only in the dynamic partition. We're going to define the components of DPR. DPR is included from static part, dynamic part, and interface. We can call dynamic part to dynamic add-ons. And in the static part, we have DPR controller and API controller. And of course, if we are gonna have some cryptographic algorithm in our DPR, we should put our algorithm in the static part of the DPR, and then have some attack on the dynamic part of it. The FPGAs can provide any necessary functionality with a cryptographic module may or may not be present. We have k distinct cryptographic cores arranged on an FPGA. Each crypto core is configurable by a set of add-ons. So we have lots of add-ons parts connected to crypto core, and since we are going to have a symmetric architecture, the number of add-ons connected to each crypto cores should be equal. Our architecture also has this disadvantage. Our disadvantage of this architecture is if one or more of such dynamic partitions are not used, it would incur a wastage of hardware resources. And it means that we will have extra hardware with extra room, with any application, without any application. This shortcoming can be solved by providing expansion slots accommodating multiple FPGA at the IoT nodes. It means that we can expand the number of our cryptographic core on our FPGA. We're going to define D-node. What is D-node? A D-node uses the reconfigurable portions for functionality enhancement as well as for interactions with other cores. And D-node has two cryptographic primitives. A TRNG or true random number generator and a symmetric key encryption hardware module. In this work, in this research, I'm gonna work on symmetric encryption module, symmetric key encryption module, and in the future work, I'm gonna manipulate the TRNG to have some other attacks. This architecture also have some benefits and some fine points that I'm gonna say them. Multiple CHS sharing a single D-node is advantageous, as this enhances the efficiency and security of the D-node. It means that when we use several CHS, multiple CHS on a single node, we will enhance the efficiency of our architecture. If the two module resides in an FPGA, the key generated from the TRNG need not to be transmitted from other nodes over the network. The key cannot be transmitted in plain text over the network, as an eavesdropper might then trivially compromise the security of the system after noting down the key, because since key cannot be transmitted from through the plain text, the eavesdropper hardly ever can compromise the security of the key. The existence of multiple functional modules on a single FPGA allows the time sharing of a single FPGA intercommunication service among the multiple modules, and then decrease the communication overhead. distribution of the CHS on the FPGA is an optimization problem, targeting two objectives, maximizing the interactions between the partitions and minimizing the number of cross-node interactions. Authentication of the D node and its components is performed using PUFs. It means that we use PUFs in this architecture to have individual, unique, authenticated D nodes. They can act as identifier generator circuits. Each FPGA has an internal master PUF and secondary PUF for functional core CHS. So each FPGA has a master PUF and each CHS has an associated secondary PUF. In this part, I'm not going to go through these PUF stuffs, because I'm going to manipulate the AES architecture. And for implementing our example, a Xilinx Virtex 5 FPGA is connected to a network over a standard 100 megabyte per second Ethernet connection. Let the CHS employed in the FPGA be a cryptographic core and the true random number generator. Considering the IoT model, one of the D node in the network consists of a crypto core and crypto generator. And we have also PLL phase lock loop to generate various type of clocks with various speed. And also we should have LFSR to apply the Trojan in our architecture. The add-ons are allowed to be reconfigured on demand on the fly by transferring the required partial configuration bitstream over the internet connection to the FPGA. Possible threats to DPR-enabled FPGA-based IoT infrastructure. We can have some threats on cryptographic algorithm and some threats on cryptographic key, and for cryptographic security, providing security, we should make these two main parts safe. We are going to insert some hardware Trojan through DPR part to evaluate if these two parts are still secure or no. Here I show I'm showing the design of the implemented hardware for attack on AES algorithm. In this part, as you can see, the plain text is going to enter to the first round, and also the plain text is going to enter to pattern detector, and then after doing adding to round detector, the bit as a trigger comes to into an XOR, and then we use the bit number 0 of the AES matrix, and then it will be changed, flipped by our hardware Trojan, and then goes into our XOR as the second pin. And then we we will put it in the bit number 0 of matrix, and after that we apply it to the round numbers 8. In round number 8 we are going to apply our Trojan. It means that before it we couldn't have any manipulation, and if we are gonna to have some changes in ciphertext, I mean have some faulty ciphertext, it means that we must apply our trigger to our Trojan to the round number 8. And the faulty ciphertext produced after the fault attack is altered by the inserted HTH. It means that we are going to piggyback the malicious component of the bit stream on the benign component bit stream to be mapped on the FPGA. It means that the privileged user can wait till a pre-scheduled and pre-authorized DPR operation is to be performed, and to add or to modify the existing circuit on the FPGA. So as I said before, we should have specific predefined, determined bit pattern in the plain text for some predefined number of times as our bit stream to apply them as our Trojan to the plain text, to our run number 8. And in this project, it has been already proved that with a single fault injection, since we are going to flip only one bit as our Trojan. With a single fault injection and with a single fault encryption, the key can be derived with a brute force search of size 232, which can be performed in less than 15 minutes using a standard desktop PC. The brute force search size can be reduced further to 28. And as I mentioned before, we can have two parts, ring TRNG and cryptographic algorithm to be manipulated. And in this part, I briefly reviewed some vital parts of TRNG, and I can take a glance on it. It means that a path which is which can be used as ring oscillator based in our TRNG, which provide authentication and unique signature. And as I said before, the PLL can create some clocks and some LFSR and so on. And in my project, I implemented. At first, I simulated an AES HTH-free architecture by FPGA. As you can see, it's plain text and it's ciphertext. And after that, I try to manipulate just a single bit on it, and then have proved that our ciphertext will be manipulated as a faulty ciphertext. And here is our implementation and design after defining the constraints. And it is our FPGA hardware, and in the bottom I showed the timing and flip-flops modeling results. And we work on the AES algorithm, and our future research would be, as I mentioned before, would be working on the key schedule. By inserting the hardware Trojan to an AES algorithm and then comparing its result with HD3, we realized that the ciphertext will be changed completely. Consequently, it shows that the security of a DPR-based algorithm is more vulnerable than the simple one. Detection techniques vary in their requirements and deployment phases, with some needing the netlist or layout description of the design, while others require an HD3 instance of the design, which isn't always feasible to obtain reliability. Thank you so much.